gone ahead and started recording. Thank you to all joining us today. My name is Ben Edelman. I am with TTI and CARTEEH, and I am going to turn over to our colleagues at Georgia Tech shortly. I just wanted to very quickly provide our attendees with a little bit of the process-oriented stuff for this webinar. So we're going to have one presentation today from Carrie Watkins and Caitlin Schaefer. At the end of their presentation, we'll have a Q&A session. If you have a question, you can enter it in the chat at any time, and I will go ahead and keep an eye on that chat to ensure that questions are captured, and I will go ahead and moderate that session as well. So you can enter a question at any time. If it pops in your head, feel free to drop it in even in the middle of the presentation, and we will circle back to it during the Q&A session. With that, I will turn it over to Michael Rogers. Michael's the lead for Georgia Tech in the CARTEEH with our CARTEEH consortium. And Michael, you can go ahead and take over from here.
All right, thank you very much, Ben. Georgia Tech is a participant in CARTEEH and a number of other of the university transportation centers. So it's my great pleasure to announce our speakers who are going to be presenting on one of the competitive research projects that CARTEEH funded in our first few years of operation. Dr. Carrie Watkins is the Frederick Law Olmsted Associate Professor of Civil and Environmental Engineering at Georgia Tech and a close colleague. We teach a number of courses together, and she keeps me somehow straight on the air. She focuses on collective and active transportation and its research, and I try to show her the way in freight, but she seems to be dedicated to these other modes. And her co-presenter is Caitlin Schaefer, who is currently an engineer at Kittleson Associates in Baltimore, Maryland, where she works on active transportation. Caitlin, during her graduate days, worked with both myself and Dr. Watkins on a variety of projects, and for her work on this and some other projects, she was the 2019 CARTEEH Student of the Year. And so it's kind of come back to CARTEEH after some time. So with that introduction, I'll turn it over to Dr. Watkins and look forward to your presentation.
Thank you so much, Mike. Caitlin and I are actually going to talk about the project that, as Mike mentioned, was funded by CARTEEH, one of the competitive funded projects, and it actually ended up being a big part of Caitlin's master's thesis. So it's some work that we're both pretty proud of. It was our first foray into air quality research, so we're glad we had lots of people at CARTEEH behind us, sort of pointing us in new directions as we went. And it was exciting to turn our love of bikes into a project where we could focus on learning something new about air quality. So let me launch right in. I'm going to give some background on the project, and Caitlin's actually going to take the bulk of what it was we actually did, our methods, our results, and then I'll come back at the end and talk about bigger picture of how we're hoping to move on from this and use it and the conclusions that we drew. So a big part of the goal in my research, and many of the students who work with me, like Caitlin, is actually to move the world of cycling from folks like this to folks like this. And there's a lot of ways that we can study those differences. We can look at actual safety and perceptions of safety, people's route choices, all of those kinds of things. And in order to do that, we've actually started an instrumented bike project at Georgia Tech called Seeing Like a Bike, or SLAB. What we've done is we've created this box, we call it the SLAB box, that has all kinds of different sensors in there to understand the environment around the cyclist, so that we can better look at issues that cyclists face while they're biking and what that might mean for getting more people to choose to cycle for their mode of transportation. So on here you can see a whole list of the kinds of sensors that we've been including. And as you see, some of those are environmental sensors, including particulate matter. And so the funding from CARTEEH allowed us to focus in on that aspect because we had already done the instrumented bike, but we had some pretty cheap sensors that were not really working very well. And this gave us an opportunity to look closer at what the right particulate matter sensors might be and learn some things that we should know in order to be able to carry on research using them. So this is a picture of our actual slab box. It gets mounted to any person's bicycle. So instead of us having an instrumented bike somebody has to ride, they get to ride on the comfort of their own bike. And this just gets attached to it. So the motivation for this particular air quality project was really about the idea that pollutant exposure can vary significantly depending on the mode and the route. So if they're choosing to cycle or some other mode and what particular route. And cyclists are particularly vulnerable to particulate matter. Prolonged or repetitive exposure to particulate matter has had many adverse health impacts, reduced lung function, asthma, heart attack, stroke, and there's limited research to understand what kinds of cycling infrastructure might actually be better or worse for cyclist health. There's really a push for safety reasons for us to put more and more bike lanes and things of that type in, but maybe we should be relying more on off-street paths, things like that, when it comes to a PM exposure, or maybe cyclists should even be in the road. So these were the kinds of things that we were hoping to take a deeper look at. So really the objective of the air quality piece of the project grouped into this larger instrumented bike project that we have was to assess the feasibility of using an instrumented bicycle equipped with low cost air quality sensors to monitor PM 2.5 exposure of cyclists. And in particular, we did this in Atlanta, Georgia. So a little bit about air quality sensors for anybody. I'm guessing there's folks on the call who know much more about this than Caitlin and I do, but just for those of you who don't, or just to understand sort of our approach to this, you'll see that the one on the upper left, that is our slab box. So we were trying to build this custom collection with all these different environmental sensors. There are sensors like the GRIM, very, very high quality research grade air quality sensors. This is not the kind of thing that you want to be sticking on the back of a bunch of bicycles. It's heavy, it's cumbersome, and it's very expensive, and you don't necessarily want to trust that we could put this thing on just anybody's bike. However, it makes for a great thing for us to test differences in cheaper air quality sensors from these sort of high quality research grade instruments. One of the ones that's been talked about a lot is the Purple Air sensor. We looked into the Purple Air. What they're trying to do is create this air quality network using Internet of Things. Part of the difficulty of it, though, is you can't get more refined data. They've sort of set certain parameters with Purple Air, and as a researcher, it doesn't quite give you the flexibility that you might want. So we actually went to the PMS 5003, which is an off-the-shelf hobbyist air quality sensor. It happens to be the sensor that they have two of in Purple Air, and we thought this was a better way to go. Then we can choose how many sensors. We can do any averaging or looking at, comparisons between multiple PMS 5003s on our own. So that was the route that we ended up going after our process of looking into all these sensors. So the PMS 5003 was selected for the low cost and small size. It facilitated data collection with the bicycle, and it had the highest correlation with the expensive commercial grade sensors used by the EPA. So that was what we ended up going with for the research that we did. But the first phase of that was for us to actually calibrate these things using this research grade through the GRIM. And so I'm going to turn it over to Caitlin to talk more about that calibration process and, again, sort of our method and results with the work that we did.
Thanks, Dr. Watkins. So What we did first for this sensor calibration is kind of two different types of tests. So we had the stationary comparison of the research grade instrument and our low cost air quality sensors, and the mobile comparison of the two. So actually putting them on a bike and seeing how they reacted when in motion. So in order to do that with the bike, we had our first iteration, a less refined version of the instrumented bicycle. So you can kind of see there's just a large basket on the front where we put the GRIM and also two of the low cost sensors, as well as a GPS and a GoPro camera. These were used so that we could locate where our readings were coming from and also review the video so we could see if there was a particularly high reading on one of the air quality sensors. We could review it and better understand what was going on there. But first, we did this stationary comparison just to see really what we were working with. There had been previous studies, like Dr. Watkins mentioned, that said that these low cost air quality sensors that we had picked out had correlated most significantly with the research grade, but we wanted to take a look at it in our own environment. So using originally the purple air systems that housed the low cost sensors, we set them out with the GRIM just to see how they reacted over time. And we also, as shown on the graph, produced a challenge sample of exhaust to see, since we knew that was a known source of particulate matter, how it reacted. So looking at this graph, that neon green color in the background is our readings off the GRIM, where all the other colors are the various purple airs that we had out there. And you're seeing that there is kind of within a reasonable range that we're getting the PM 2.5 readings. However, one thing to notice is definitely with the challenge sample, the GRIM is much more reactive. It spikes, the quickness of response and the magnitude of response were much higher in the stationary comparison. We also, using that bike that we showed previously, did some tests in motion. So what you're seeing here is some graphics of the routes, the test routes we ran, and the colors are representative of the difference between the readings on the GRIM and the low-cost air quality sensors. So for the most part, the segments are in this green color, indicating that we were seeing similar readings off both the GRIM and low-cost air quality sensors. However, there were some areas of red and orange that were concerning when we first looked at it, but because we had that GoPro and were able to locate the GPS data, we could review the information and found that those are actually when sources such as heavy duty vehicles were passing the cyclists quickly, and you have a really sharp spike from the GRIM, but not as sharp from the low cost air quality sensors. So the overall conclusion from these initial tests were that the low-cost air quality sensors were producing similar trends, but kind of a difference in magnitude and quickness of response. And when in motion, the sensors generally agreed for most distances, with some sharp spikes that we had to keep in mind when doing our study. So we decided to move forward using these sensors and concluded that they could be representative of observed patterns of PM 2.5 exposure. So here is the more, I guess, refined instrumented bicycle with the front component and the rear component labeled. And in our front component, we had the compute functions in the Arduino Uno, and then in the rear is where the sensors and the Raspberry Pi, which were used to then output our data, are housed. And this, as I think Dr. Watkins said before, can be fitted on anyone's bike. It didn't have to be this blue bike that was used. We used all of the participants' personal bicycles. and we're able to attach these. So in order to do the data collection, we were monitoring the PM2.5 concentration along routes composed of different types of cycling infrastructure all around Atlanta, and then using that data in order to map the exposure and map it back to the different types of cycling infrastructure we see in our city. So here is, we had 4 different route options in this study. That was actually originally selected because this air quality component is part of a larger study that seeks to have riders of different abilities throughout the city. But we decided to use that to our advantage to really capture a lot of different types of cycling infrastructure. And you can kind of see they're throughout the city, and all 4 of them have different types of cycling infrastructure that are shown on the next slide. So here are all of the images of what the streets look like that our riders were actually on, and then we can go through one of them so you can get a clear idea of how the separation between cyclist and vehicle varies along a rider's route. So in this first route, which was labeled Route 2, you go to Piedmont Park. I didn't get you hit it. Yeah, Piedmont Park, and it's a separated path. It's within a park, and it's surrounded by trees, and you can't see cars when you're in the park. And then you transition to the 10th Street cycle track, which is has a small buffer of the cycle track, but you're still riding within the road. And then you transition onto a residential street. You're riding with traffic, but it's low volume and low speed. And then turn back into a bike lane, so you're on street again without any buffer or separation. And then in your final leg of this route, you're integrated fully into traffic, riding on a multi-lane street with the flow of traffic. And then you come back to 10th Street and ride with traffic back into that cycle lane eventually. So this is just one example, but it's pretty representative of our 4 different routes, and I would say pretty representative of the different types of infrastructure we have in Atlanta. So the participants could elect to ride which route they wanted to ride, and each of our routes was completed at least 5 times, if not more. So we had 27 runs when we stopped data collection for this particular part of the study, and that provided us with over 20,000 different data points of PM2.5 concentration. In addition to all of the sensors on the bicycle, we also recorded the start time, a background concentration from a nearby monitoring site, the temperature, wind speed, wind direction, and relative humidity. So in order to correct for the background PM2.5 concentration that we were getting from a nearby monitoring site, we subtracted that from our readings. And we did this because within the urban area in the region, there's already a baseline particulate matter concentration, and we wanted to see what additional exposure cyclists were receiving on our routes. So in addition to correcting for that, we also segmented our routes. So not looking at each data point that was collected every 5 to 7 seconds, I believe, but looking at segments of a whole. So where are the roadway characteristics changing? Where is the type of cycling infrastructure changing? So we identified where those were and where our intersections were, and each of our routes ended up having about 30 different segments that we averaged the concentration over. And for each of those segments, we assigned it a cycling infrastructure type and a functional classification. So we were able to produce these exposure maps for each of our routes based on the segmentation. So what you can see here is this dark green and light green color, which is showing segments with concentrations that were less than or equivalent to the background at the time of the ride. However, you can also see areas of orange and yellow that indicate cyclists were exposed to higher concentrations of PM2.5. And in order to learn more about the segments and why that might be, we used regression analysis on the next slide. So this kind of gave us a way to look at all the different variables we were exploring and identify which ones were significant. So in addition to the variables you see here, we also looked at a few different ones, including distance of the cyclist from the travel lane, number of travel lanes, speed limit on the roadway, and things like that, and found that they were mostly encompassed by this cycling infrastructure, functional classification, and land use variables. And what you're seeing on this slide is one of many iterations of a linear regression model. And in the final iterations, we decided to use dummy variables as opposed to categorical variables. So what you're seeing here is these dummy variables. So the cycling infrastructure, for example, is a simple yes, there was cycling infrastructure on the roadway, or no, the cyclist was traveling in the lane with the vehicles, as opposed to the categorical variables, which actually distinguish between the different types of cycling infrastructure. So the shared lane, the bike lane, the buffered bike lane, and the separated path. So from here, you can see that the cycling infrastructure, if it was present based on this coefficient, you're seeing lower concentrations of PM2.5, and that showed up as significant in this model. Additionally, from the coefficient of the functional classification, if the cyclist was riding on a minor roadway, they were exposed to a lower PM2.5 concentration. This was good confirmation for us because we know that on major roads there's higher vehicle volumes and therefore greater concentrations of particulate matter. And finally, we also looked at land use, which was one of the most significant findings of the regression analysis, that if the segment was located in a commercial area where there are storefronts and restaurants, the cyclist was riding in an area where there was higher particulate matter concentration. Additionally, highlighted on here is the shaded weather characteristics, so temperature, wind speed, and relative humidity. And those were important to include as well because we know that those can be very impactful on the air quality. Another way to show our segmented analysis were just these basic plots of those three final variables I just went over. So the cycling infrastructure, you can see that no cycling infrastructure was had a greater concentration than the cycling infrastructure. However, they were kind of within the same range. Same for functional classification, but where you see the greatest difference is looking at that land use. Again, and you see the commercial land use having higher concentrations overall. The little shaded area at the bottom of the plot is just giving kind of a reference point for the concentrations we were seeing. So the majority of the concentrations we observed in this study were below the 10 micrograms per cubic meter that the World Health Organization indicates can be harmful to people's health. However, particularly in the commercial land use, we did see some exceeding those values. So I will hand it back to Dr. Watkins and she can give the main takeaways from our study and what else came out of this work.
Sure, thanks, Caitlin. So in conclusion, what we saw from this particular study was that lower PM2.5 exposure was observed on these designated cycling infrastructure. and also on roadways with the lower traffic volumes. But as you saw in the linear regression, for the cycling infrastructure, it was sort of borderline. It was one of those things we were hoping to see a stronger response there. Our hypothesis was that we would see a notable difference, and it was kind of right on the edge of being significant or not at the 0.05 level. Land use, however, specifically commercial areas, was one of the most significant indicators. So cyclists going down a street, like in the example that Caitlin showed, like Peachtree, where there's a number of different restaurants and such, it definitely affected the PM 2.5 levels that they were being exposed to as they were biking down a road like that. So this is often the places where the demand for bicycle infrastructure is greatest, because those are the destinations that those very cyclists want to be going to. So it's something to keep in mind where changes in infrastructure design could be made. Cyclist PM 2.5 exposure was more impacted by the meteorological variables, which was something that Dr. Rogers warned us about right from the beginning, that we were hoping to see all these things, but it had much more to do with meteorological variables that were changing the background concentration than any of the actual things that we were seeing with that on-road exposure to higher traffic volumes or even the commercial areas. And this is all in alignment with previous instrumented bicycle studies and pollutant exposure studies. So although our techniques might have been a little bit different, trying to use these lower grade sensors or trying to do this on an actual instrumented bike with the cyclist riding and such, that might be a little different from previous studies. We were actually seeing some pretty similar results to what others who've come before us have seen. So how are we actually going to use all of this? We've now got those sensors in our in our slab box for when we're doing further studies. And so we're collecting more and more data as we continue to do studies using the instrumented bike. And that data can be made available for folks who are trying to look. We were trying to learn just enough about air quality that we could figure out what the best sensors for this instrumented bike are. But this is not exactly our area. So we're happy to share data with folks on the line or watching the video who do a lot of air quality work and would like to be able to do deeper research using this kind of thing. Our goal was to perfect our data collection method, which we think we're getting there. We are doing many other things with the slab box. So some examples, we're actually looking at stress and speed using the GPS data. So we've done some different studies in Delft with another instrumented bike, one of my PhD students, and here in Atlanta, looking at differences in speed of cyclists and how much they feel like they're forced to go faster to keep up with the car traffic if they're put in with that car traffic in American cities as opposed to cities abroad. And we're looking at things like what people say stresses them out as they're cycling and verifying that with some of the data that we have from the sensors. We're also using components like LiDAR to be able to look at things like close pass events and understand how people rate that in terms of stress and general sentiment about whether they feel that drivers notice cyclists and the type of cyclist they are, and see how big of a deal these close pass events seem to be from cyclists. And we're also looking at new ways to measure stress. So in the past, we've been having folks actually say how stressed they are on different segments. So we pause as they're going through a route on the instrumented bike and we have them indicate their stress level, and then we can tie that to other things. But we're looking at using things like eye trackers to actually come up with a measure of how stressed they are as they're cycling. And so this is an eye tracker that we've been using, and some examples of how it uses cameras pointed forward and at the eye to look at where the eye is pointed, so we can look at how wide of an area people are taking in as they're cycling, what they focus on, how long they focus, different things like that in order to try to understand their perceived safety and their stress level and things like that. So these are all aspects that we're using the instrumented bike in general, and we're combining some of that environmental data into all of the different sensor readings that we're getting. So with that, that is what we have to present, but we're happy to take questions. Here is Caitlin and I's contact information. And I just lost the screen. Did you take it back, Ben? Or wait, maybe I should.
No, I still see it on the screen.
Okay,
Oh.
I think something happened. I don't know. It all of a sudden changed on me.
It did just unshare.
Yeah.
We'll send that out with the presentation after, so that everyone has your contact information. But
okay.
First and foremost, I just want to say what a wonderful presentation. So well presented, so thoughtful. Obviously, excellent research. The research has been published on the CARTEEH website. So if anybody is interested in really doing a very deep dive, that is on the CARTEEH website under final reports. And we also have a one-page short version of the research that we've published as well. So thank you very much, Carrie and Caitlin. We have a couple questions. So first question is from Tim Hunt. He says, nice study, I concur. What percentage of time were the cyclists in areas above 12 micrograms or even 10 micrograms when they did their routes?
So if I can reshare, probably the easiest way to answer that is back to that graphic. Let me see if this works. Okay. Are we good? Can you see the screen, Ben? Okay. Yep. So I don't know the actual percentage, and I'm guessing, Caitlin, do you know the actual percentage?
No, I don't know the percentage.
Okay. These box plots, I believe Caitlin was doing a traditional box plot where it's a 25th percentile, 50th, and 75th percentile. Is that right, Caitlin?
Yeah, that's correct.
Yeah. So you could get an idea of that from these. I mean, just looking at these 50th percentile, I don't know that my math is good enough to do it that quick, but I would say it's, maybe 10% of the time, something like that. So it was not a good deal of the time that they were out there. Most of them were below that 10 level. But we definitely had readings, including some, as you see on here, that were really, really high, like at the 30 micrograms per cubic meter level. So
great. We have a comment from Tim Wood. He says, thank you, this is very informative. He says, I might suggest using the 24-hour PM2.5 standard rather than the annual PM2.5 standard, since you're measuring short-term exposure. Carrie or Caitlin, did you have put any thought into using the 24-hour PM to the 24-hour PM2.5 exposure instead?
No, that's an excellent point, and I think that this is an example of our lack of air quality data work before this that's coming out. I'm curious, I don't know if we can unmute people or anything like that, Ben, if Tim wants to share with us how much higher, or Mike Rogers probably can share with us how much higher the 24-hour standard is.
Yeah, I think the purpose of research, Carrie, wasn't really to establish violations, but rather to establish whether or not the question of whether people who are engaged.
I think we lost Mike.
Oh, no.
I'll follow up on what I think he was about to say. So the purpose of our research was really to try to understand more about the bike infrastructure. Oh, thank you. I see that Tim put it in the chat. And 24-hour standard is 35. As you can see on this graphic, we had very, very few points, if any, that were that high. But really what our goal was not to actually look at how much they were exposed to. And I could see how others might actually want to look at that, right? There's lots of big questions out there about, you know, am I better off cycling or not cycling, right? The physical exertion and such is great for me, but if there are particular times of day when I'm going to be exposed to that high of a level, maybe I'm better off not actually biking. It's better for society if I choose to bike, but for me individually, there may be points in time where it's better if I don't. What we were really trying to get at was like that cycling infrastructure, the levels of traffic, those kinds of things. We were trying to understand the environment around the cyclists and what kind of infrastructure is better for them rather than actually those sort of raw levels that they were exposed to. And I think that's kind of what Mike started to say. We lost you for a minute, Mike, so I don't know if you have something else to add. Oh, we lost him completely now.
Yeah, I think his internet dropped out. Okay, great. No, I think that was an excellent explanation. So Tara Ramani also says, great presentation. She asked, did you consider or are you planning on including sensors for other pollutants into the slab box in the future?
Yeah, so we had tried a few others, and I think if there's folks who have recommendations of you know sensors that we should be trying for other environmental pollutants, I think our foray into particulate matter taught us that there's a lot of intricacies to this and calibration and such that it's really, really hard to just throw some of these sensors on an instrumented bike and hope that you're going to get useful data out of it. And so I think, you know, in the future, as we try to include more environmental sensors, we're looking for collaborations where we could actually, you know, work with researchers who can educate us about these different environmental sensors so that we're getting the right ones. Because my team knows a lot more about GPS and LiDAR data and those kinds of pieces. So short answer, yes, we are looking into that, Tara, but I think we haven't made great strides in any of them yet, outside of the study you're hearing about. So.
Great, thank you. Quinn Yang has a question. Says, we have a project in New York City looking at bicycle commuters, and that PM 2.5 has been monitored for several 24-hour sessions, including 1.5-hour intervals on roads to and from work. Said that I am surprised that in your model, time of day was not a significant variable. Were any data collected during rush hour versus non-rush hour? And were there any insights or trends from that?
So I'll start to answer this one, and then Caitlin will jump in and correct me if I'm wrong. But I think the reason that it was not significant is because we were using the difference, like we were subtracting out that background concentration. And so that's what would have changed, right? It would have been higher different parts of the day. Correct me if I'm wrong, Caitlin, in that.
Yeah, I believe that's correct. There's also a limitation within our data collection was that we were having people volunteer for this, like on their own time. So the diversity of when we also had participants riding was not really when they were commuting to work. It was like in the morning before they go to work or things like that. So even when we looked at models that weren't correcting for background concentration, it wasn't as significant as if you're doing like the 24-hour study throughout the day, I would think.
Yeah, thank you. And Kiang, I apologize if I mispronounced your name, but I think that we'd all be very excited to see the results of your folks' study in New York City, and understand how those compare to what our presenters found. It looks like we have one more person typing, so we'll have one more question. But we do have some more time for questions for our presenters. So if anything comes up, please feel free to enter into the chat box. And we'll give Tim Hunt is in the process of typing, so we'll give him a quick minute. And oh,
We got 2 of them.
We got 2. Oh, and Kyung said that results are on the way, and they're happy to learn more from your project. We're excited to see those, Kyung. Thank you. So Tim Hunt mentioned, I said you mentioned a GoPro camera. Did you correlate images of diesel vehicles passing with levels?
So we don't actually use the GoPro. Like the standard slab box setup doesn't have the GoPro on it. We were using the GoPro because we were seeing these differences from the GRIM readings when we were trying to do the calibration piece of this and understanding how well the low grade sensors were working. Caitlin, again, jump in, but so we did use the GoPro to correlate that with like different vehicles passing. If it was like a bus on campus or something like that, that likely had diesel. We were doing that when we were trying to understand how well the sensors worked, but then we didn't do that later in the data collection piece.
Yes, that's correct.
Great, thank you. So we'll wait just another quick minute. We have we're at about a quarter of, and I think everyone would not complain if we were get to end a little bit early. Again, such an excellent, concise, and well put together presentation. That's how we leave so much time for comments and questions. So
we took a bunch of slides out, Ben. I think we were faster than we thought we were going to be. So sorry about that. We actually could have talked more about variables we tried and didn't use, but we thought people probably want to know what worked than what didn't.
Yeah, no, I appreciate it. I think that the Q&A is excellent, and it's always hard to figure out how long you're going to take, especially in these virtual environments. Sometimes it's hard to get a pattern as you move through. So we do have a couple more folks that are typing, so we'll have a couple more comments and questions for you coming up.
Ben, I got knocked off a little bit earlier. I wanted to sort of put some of these competitive research programs in context. We're obviously looking at this active transportation component. We also did a project where we're looking at special exposures associated with particular environments. We talked about this active transportation. There was another research project which focused on some occupational exposures at major transportation facilities. And there's another project that focused on paratransit and the potential exposures for people who were dependent on paratransit for activity, especially associated with the long time spent loading and unloading of passengers. And so these were intended to look at how well our models of exposures, looking at people's movement through the environment, how these might be modified by their particular activity choices to help find these models. And in this case here, part of the reason for looking at this increment, this change from the background, was to evaluate how much the physical activity and the conditions would represent a change from the normal environmental conditions you might see.
So it looks like Kyung did say that BC would be a good addition to measure traffic, although BC monitors are a bit expensive. So that's one thought.
Yeah, this was actually something that Caitlin and I learned a ton about in attending one of the CARTEEH conferences, was that we were focused on particulate matter. And then lots of folks had brought up the fact that black carbon is really what we need to be worried about. And so I totally agree that it would be interesting, but our findings so far, like, we didn't look into the sensors too much, but it seemed that it was much harder to find these kind of, hobbyist grade black carbon sensors that we would be able to put in to something like the instrumented bike project. So we didn't pursue it any further when we started looking at it, and we stuck with the PM2.5. And at that point, we were pretty far along in our study anyway. But it's a great point that, as similar things are done with black carbon sensors, that's absolutely what the cyclists should be more worried about than PM 2.5. And then I can just take the next one if you want, Ben, and comment to Tim's comment. Yes, absolutely. Tim said that, as we know, cycling infrastructure has safety benefits that are significant compared to any air quality benefits. And that's the bulk of my research, Tim. The goal here was really for us to understand there might be different ways that we can separate out cyclists that actually would still provide the safety benefits, but might do a better job with air quality at the same time. And that was kind of what we were trying to get at here was there's been a push for cycle tracks, for, sort of these in-road bike facilities, and maybe having something that has a little bit more of a separation where there's actually, small plants or something like that, that this makes a big difference in separating those cyclists from the traffic that they would be exposed to. So we were trying to get to the intricacies of that, but as you probably noted through the presentation, it was hard for us to see like that much of a difference. And part of it, I think, is also being in Atlanta, we only had so much cycling infrastructure that we could be testing. So it would be interesting to take our instrumented bike, our boxes on the road, or collaborate with researchers in other places where they have a lot more cycling infrastructure that we might be able to replicate the study and see even more interesting things.
Absolutely. Thank you. So it looks like we don't have any other questions. I think now is a good time to wrap up. If I see anybody typing as I'm closing up shop, I will go ahead and allow that last question, but I don't see anybody typing as of right now. So on behalf of CARTEEH, TTI, and everyone here, thank you, Mike, Caitlin, and Carrie. Excellent presentation. For those folks in attendance, just FYI, we are recording the webinar, and we'll post it on the CARTEEH website. So if any of you think that your colleagues, friends, or family members would be interested in this presentation, please feel free to send along. Our plan is to also send an email blast to our to our mailing list to let them know that the presentation has been posted, and they can view both the presentation as well as the recording anytime. So with that, we will go ahead and close up shop. Again, thank you so very much to our excellent presenters, and we'll see you at our next webinar. Thanks, everyone. Take care.
Thank you.